The next component of a transformer we'll be covering is attention. Attention in AI, especially in transformer models, is a way the model figures out how important each word or token is to the meaning of a sentence, particularly in relation to the other words around it. Let's reuse the sentence "I heard a dog bark loudly at a cat" to explain this better. Self-attention: imagine each word in the sentence shining a flashlight on the other words. The brightness of the light shows how much one word should pay attention to the others when understanding the sentence. For bark, the light might shine brightest on dog because they're closely related. Encoder's role: in the encoder part of a transformer model, attention helps decide how to represent each word as a number or vector. It's not just the word itself, but also its context that matters. For example, bark in the bark of a tree would have a different representation than bark in "I heard a dog bark" because the surrounding words are different. Decoder's role: when generating new text, like completing a sentence, the decoder uses attention to figure out which words it already has are most important for deciding what comes next. If our sentence is "I heard a dog," the model uses attention to know that heard and dog are key to adding the next word, which might be bark. Multi-head attention: this is like having multiple flashlights, each highlighting different aspects of the words. Maybe one flashlight looks at the meaning of the word, another looks at its role in the sentence, like subject or object, and so on. This helps the model get a richer understanding of the text. Building the output: the decoder builds the sentence one word at a time, using attention at each step. It looks at the sentence so far, decides what's important, and then predicts the next word. It's an ongoing process, with each new word influencing the next. So, attention in transformer models is like a guide that helps the AI understand and create language by focusing on the most relevant parts of the text, considering both individual word meanings and their relationships within the sentence. Let's take a look at the attention process. Token embeddings: each word in the sentence is represented as a vector of numbers, or its embedding. Predicting the next token: the goal is to figure out what the next word should be, also represented as a vector. Assigning weights: the attention layer looks at the sentence so far and decides how much influence each word should have on the next one. Calculating attention scores: using these weights, a new vector for the next token is calculated, which includes an attention score. Multi-head attention does this several times, focusing on different aspects of the words. Choosing the most likely word: a neural network takes these vectors with attention scores and picks the word from the vocabulary that most likely comes next. Adding to the sequence: the chosen word is added to the existing sequence, and the process repeats for each new word. So, let's use GPT-4 as an example for how this entire process works, explained in a simplified manner. A transformer model like GPT-4 works by taking a text input and producing a well-structured output. During training, it learns from a vast array of text data, understanding how words are typically arranged in sentences. The model knows the correct sequence of words but hides future words to learn how to predict them. When it tries to predict a word, it compares its guess to the actual word, gradually adjusting to reduce errors. In practice, the model uses its training to assign importance to each word in a sequence, helping it guess the next word accurately. The result is that GPT-4 can create sentences that sound like they were written by a human. However, this doesn't mean the model knows things or is intelligent in the human sense. It's simply very good at using its large vocabulary and training to generate realistic text based on word relationships. So, that's an overview of attention in a transformer model.